You've probably heard the word nanotechnology before, but the truth is, it's not what most people imagine. Is it the tech inside of Tony Stark's suits in the Iron Man movies? Is it gray goo that will eat the entire world? Is it a secret technology the government's hiding from us? Or is it the next big thing in engineering, the ultimate way humanity shapes matter and controls the physical world? My name is Jason, and I'm a sci-fi and sci-fact filmmaker, and I've been interested in nanotechnology for the past few years. But I hadn't seen a lot of progress, so I spoke with the scientists trying to make nanotech a reality and asked them some questions. So in this video, we'll zoom way in to the atomic level to understand what the state of nanotechnology really is.
The strange thing about physics is that for the fundamental laws, the applications of mathematics to physics, it's perfectly natural that the mathematics will be useful when large numbers are involved in complex situations.
In the world of software, the holy grail, the final problem to solve that fixes all the others, is thought to be AI, intelligent systems that can iterate upon and beyond themselves. But that's in the world of bits. What about the world of atoms? For the physical world, that dream lies in nanotechnology, where you could work with matter at the atomic scale, building molecules and whole structures, atom by atom. Technically, nanotechnology is a wide array of different things. What I just described is atomically precise manufacturing, or APM, the ability to place atoms exactly where you want them. And that's what we're exploring in this video. But where did that vision first come from? And when can we expect it to be a reality? If this really is the final frontier of hardware, why aren't we pursuing this the way we're pursuing AI? Well, the first step I took to answer that question was to find out who are the people working on the frontier of nanotech. And that led me to Dr. Jeremy Barton, a physical chemist and nanotechnology pioneer.
We have nanotechnology in our computer chips, in the electrodes of our batteries, in our TVs. We have existence proof of nanomechanical technology, intricate systems of nanomachines working together in order to do chemistry and move things around. But we call it life. We are made up of quadrillions of nanomachines. The scale of the technology is identical to the scale of the fundamentals of life.
Norio Taniguchi was a Japanese scientist and the first to explicitly use the term nanotechnology in 1974. Nanotechnology mainly consists of the processing of separation, consolidation, and deformation of materials by one atom or one molecule. In this single sentence, Taniguchi is essentially predicting the field of atomically precise fabrication. The term lay dormant until it was revived in the 1980s by other scientists. But in 2025, I asked Dr. Jeremy Barton how APM might work practically.
You take a reactive molecule, a small cluster of atoms that if they touch something else, they will stick to it. And with positional chemistry, you control how that moves such that it only touches the atoms you want it to react with. So you can think of it like a 3D printer. You're putting atoms in specific locations in 3 dimensions by controlling where they go. And they stick there and they stay. That's positional chemistry. The nanomachines are building very small devices that can do that work, that can actually position atoms or larger molecules and assemble them into more complicated structures.
The wild thing about our current working theory of nanotechnology is that it is eerily similar to how we do manufacturing at the human scale. At the nanoscale, we're in the business of trying to build nano components, manipulator arms, rotary motors, feedstock systems, positional control systems. The list goes on. But in order to move atoms around, first you have to know where they are. You have to see them. And that led me to another researcher in the field, Felix Benneman, who is working on how we can look into the world of atoms.
What I'm working on is electron microscopy. So electrons have a much shorter wavelength compared to photons. The acquisition time for imaging them isn't actually that long. You have your sample that's on the nanoscale, so you have a few hundred atoms, maybe 1,000 atoms. You have a convergent beam, this is called STEM imaging with the electron microscope, and you scan it over the area. For this level of resolution where you actually want to see atoms, the main techniques are electron microscopy. There's a completely different area, which is called STM or AFM. And so you move this tiny needle over the sample, and whenever there's a bump, you correct. And so it moves over the surface Basically, in the current, you see the bumps. That's how you measure the surface in 3D as well at this kind of resolution. However, if you are looking at a crystal structure, which is actually a much bigger structure, but you want to zoom into a tiny region, then you have more techniques. X-ray crystallography, for example, and you could do electron crystallography.
So this is some of the super high-level theory on how APM could work. But in the year 2000, the US government hatched a plan to make it a reality. But it didn't exactly work the way they intended. But before we get to that story, we need to understand the history of how scientists thought about nanotechnology before they brought it before the President of the United States. To do that, we need to go back, way back. Around 460 BC, the Greek philosopher Democritus proposed that all matter was composed of tiny invisible units called atomos, which means uncuttable. These atoms, he imagined, came in different shapes and sizes and combined to form all visible things. But it would take 2 millennia to make any real progress in understanding them. In 1827, botanist Robert Brown had observed tiny pollen grains jittering randomly in water, a phenomenon later called Brownian motion. For decades, no one could explain it. Then in 1905, Albert Einstein published a paper showing that the random motion could be explained by countless invisible water molecules colliding with the pollen grains. Using statistical physics, he derived equations predicting exactly how far and how fast the particles should drift, if Democritus's atoms were real. French physicist Jean Perrin put Einstein's prediction to the test. He suspended tiny resin or latex spheres in water, tracked their movements under a microscope, and statistically analyzed thousands of displacements. The observed motion matched Einstein's predictions, providing the first quantitative experimental confirmation of the existence of atoms, convincing even the skeptics that Democritus had been right all along. Through the 1920s and 30s, quantum mechanics and atomic theory established that matter is made of atoms, arranged in specific structures, setting the conceptual groundwork for manipulating matter at that scale. By the 1930s, the atom was no longer an idea. It was the blueprint of reality itself. But the real birth of nanotechnology came in 1959, when physicist Richard Feynman introduced the concept of nanotechnology in his famous Caltech lecture. Feynman proposed that one day we could arrange the atoms one by one the way we want them. He imagined tiny machines building smaller machines, cascading down to molecular scale, what he called molecular manufacturing. While no one could yet do it, the vision was planted, the manipulation of matter at the atomic scale. The frontier of nanotechnology shows us that even at the small scales, great change comes from people daring enough to build. And that's the kind of work the sponsor of this video, E1 Ventures, champions. They support deep tech founders across fields like AI, robotics, and advanced materials, helping bring ambitious ideas to life and shaping a future built not just with progress, but purpose. If you're building something bold and looking for investors dedicated to backing your vision and journey, reach out to E1 today.
There's plenty of room to make things very much smaller than we ever made them before. It turns out to be possible to build a computer in which each bit or each little piece of information is 1 atom large.
And finally, in 1974, you remember, Norio Taniguchi coined the term nanotechnology. Then, in 1981, Gerhard Binnig and Heinrich Rohrer invented the scanning tunneling microscope at IBM Zurich. For the first time, humans could see and move individual atoms. Then, in 1986, Eric Drexler published his seminal work, Engines of Creation, the Coming Era of Nanotechnology. He expanded on Feynman's vision, describing molecular assemblers and self-replicating nanomachines. Drexler's molecular manufacturing vision was very specific: programmable control of chemical bonding to build complex structures, machines that build machines. Later in the 80s, we moved from theory to application as a team of IBM scientists, Don Eigler and Erhard Scheitzer, spelled out the letters IBM using individual xenon atoms.
Initially, this was physicists trying to figure out what they could do with their tools. That then gets extended when the physicists bring in chemists to work with them, who figure out that if they make a particular weird molecule and put it on a surface, then they can apply voltage to drive off a bromine atom and make the thing reactive and do more chemistry.
I think a lot of people in the semiconductor industry consider themselves as working in nanotechnology, actually. To build 3D structures today, you use the UV lithography. That is the best way, and the semiconductor industry has perfected that.
From the 1950s to the 1980s, we made an astronomical jump in taking nanotech from theory to practice, actually beginning to move individual atoms around. And as computational power and software improvements began to fly up and to the right, it seemed we were simultaneously unlocking everything we needed to make atomically precise manufacturing a reality. And that's exactly what the United States government thought when they launched the National Nanotechnology Initiative at the turn of the millennium. The nanoscale is not just another step towards miniaturization. Developments in these emerging fields are likely to change the way almost everything, from vaccines to computers to automobile tires to objects not yet imagined, is designed and made. Those are words from the founding document of the National Nanotechnology Initiative from 2000, and we got to talk to the guy who was a pivotal part of putting it all together, Tom Khalil.
The National Nanotechnology Initiative, which President Clinton announced in a speech he gave in January of 2000 at Caltech, resulted in over $40 billion in funding for nanoscale science and engineering and the creation of the field of nanotechnology.
So the government agreed nanotech was a big deal. The NNI was founded, and it was supposed to be pursuing this dream of atomically precise manufacturing. But wait, that was back in 2000. What progress have we made since then? Well, turns out a lot, but not a ton specifically for atomically precise manufacturing. Remember at the beginning of the video, I said, technically nanotechnology is a wide array of different things. And the definition of those different things all comes down to size. Paint me a picture of just how small nanotechnology is.
Anything smaller than 100 nanometers is nanotechnology, per the NNI definition from 20-odd years ago.
Biotechnology mostly works at the cellular or molecular level, sizes of tens to thousands of nanometers. Nanotechnology works at the atomic level, 1 to 10 nanometers, significantly smaller. The smallest biotech tool, like a lipid nanoparticle that carries a vaccine, is still hundreds of times bigger than the atomic scale structures nanotech engineers aim to build.
The easy comparison is a hair. So if you take a tenth of a millimeter being a hair, so it's 100 micrometers. So you take 100th of that, then you add 1 micrometer, and that's still 1,000 times bigger than a nanometer. We're 9 orders of magnitude out from a meter under a microscope. Even from that scale, it is such a huge gap to actually the nanoscale.
When the NNI was created under the Clinton administration, its definition of nanotechnology was understanding and control of matter at dimensions between approximately 1 and 100 nanometers. That language intentionally cast a very wide net. It included quantum dots, nanoparticle coatings, nanocomposites, thin films, and so on. Any technology where nanoscale properties mattered, even if it wasn't atomically engineered. This definition folded in huge portions of material science, semiconductor R&D, and biotech. In the NNI's first 20 years, they distributed over $30 billion in funding. And as a result of the breadth of size, the majority went to bio-related and materials projects, drug delivery, nanosensors, nanotoxicity, and safety, not molecular manufacturing. This happened because biotech and life sciences were seen as immediately useful and fundable, while the idea of atomically precise assemblers was viewed as speculative or even science fiction. Policymakers wanted near-term deliverables, safer coatings, better imaging, nanomedicine.
The vision that some folks had about the sort of long-term promise of atomically precise manufacturing, I think that was a very exciting vision. I'm not sure that it was like broadly shared by the scientific community. Now, the problem is you might have this really lofty long-term goal, like the idea of having self-replicating robotic factories. That's going to take a long time. You have to say, like, how do we make progress towards that goal? Because your longer-term aspiration may not be in the adjacent possible.
But the dream didn't die. It just got delayed. There are still a bunch of people pushing the frontier to achieve APM. But just how close are we to APM? And what has to happen to achieve it?
We need to be able to control motion on a molecular scale and to control the chemistry that's driven by that motion. Right now, we don't have very much capability in this space, right? We can control things by changing like the pH of a vat. We don't have the ability to build a nanorobot arm that actually can operate. Like the initial requirement is, can we build a nanorobotic arm, essentially, that you can use to assemble not atoms, but relatively large molecules or nanomaterials together into something else. Long-term objective is, build something that can build anything. I want the technology's capabilities. I want us to no longer have to worry about diseases. I want us to no longer have to worry that we only recycle 7% of the material we pull out of the earth, that we have material limitations. I want us to be in a position where colonizing Mars is actually a reasonable thing to do and actually relatively easy. And so I want us to do it right and responsibly.
Nanotechnology is in our world already. Since the 2010s, nanotech has been widely integrated into everyday consumer products. In sunscreens, titanium dioxide and zinc oxide nanoparticles scatter ultraviolet light. Nanocoatings make fabrics water and stain repellent. Quantum dots in QLED televisions and smartphones produce pure colors and improve brightness. But that's something entirely different from nanoscale assemblers building anything at the atomic level.
If we can put atoms where we want them, but we can only do it one atom at a time, 1 atom per second, it will take a very long time to build anything useful. So the nanomachines are about saying, can I get 1 trillion devices, each of which is doing this process, so that we can put enough atoms in place to make things really, really useful. So with the exponential assembly, you get to the point where you have enough devices to build cars, or clothes, or full-scale computers. Nanomachines by themselves, once we have them operational, and at small scales, can do amazing sensor work. They can accelerate biomedical research. They can be used for certain small-scale tasks, but without the scaling up to quadrillions of devices, they're still too small to really affect anything other than very high-value products like computer chips.
If we figure out APM, the ripple effects can touch everything. Energy, materials, medicine, computing, stronger materials, faster chips, more efficient manufacturing.
The idea is we can take the same principles, but apply it to our entire technology stack. So instead of just building better medicines, can we build better computers? Can we build better filter to purify waste and eliminate pollution? Can we build better systems to pull CO2 out of the atmosphere?
If we crack APM, it would be an incredibly powerful tool for humanity, completely changing the way that we build. But at the same time, the risks of playing at the nanoscale are big.
We're trying to change the world to make it a better place for us and our kids and everybody to live in. I think any new mitigations or risk mitigation measurements we bring up need to be integrated with our existing system. We shouldn't just try to start from scratch to minimize the odds of something bad happening. And in the early days, very few bad things can actually happen. The technology will not be the scary sci-fi stuff. When we get towards the scary sci-fi stuff, I hope to God that we have spent enough time with the technology to be iteratively improving our social integration and ethics on the topic.
When people imagine nanotechnology gone wrong, the first thing that can come to mind is the science fiction nightmare. Swarms of self-replicating nanobots turning the world into gray goo. Basically, a microscopic assembler starts copying itself endlessly, consuming raw materials in the environment to make more nanobots. A single self-replicator multiplies into trillions, converting the biosphere, plants, animals, everything in it, including you and I, into a uniform gray goo. It's not unlike the AI doomsday paperclip machine scenario, but there are other risks as well, more subtle, and in many ways, more dangerous. Nanoparticles are so small they could slip past our body's defenses through skin, into lungs, and across the blood-brain barrier. What seems harmless at bulk scale can become toxic at the nanoscale, and once released into soil or water, these particles don't just disappear. They can persist, spread, and accumulate in any given ecosystem. Atomically precise manufacturing could make unstable molecules or materials that spiral out of control, and the same tools that might cure disease could also be weaponized. The biggest risk of moving too fast might be failing to think deeply about how to develop this new technology in a safe way. The time to think and talk about that is now.
My personal inclination is that we try to keep the basic components of the technology open and broadly available. We try to ensure that when people improve those basic components, they have to give it back to the community one way or another. but that more broadly we put in place something like there are no replicators that replicate in the environment. Nothing that you can accidentally release in an industrial spill that could go on and do a gray goo scenario. You would have to deliberately design something like that. Try to ensure that the production capabilities are such that when somebody has an accident, that it's easy to clean up. You have no idea how to make things perfectly safe from the very beginning. But you can give your best guess estimates to the support systems.
Although the current state is maybe not what's portrayed in science fiction, to some extent, we are further in some areas where science fiction doesn't really show. Or what we're doing in Oxford at the moment is, for example, reconstructing these atomic structures in 3D and so on. That's really quite special.
I want to see what humanity does, but this is about more than the technology. We've got all of the human side that we have to pay attention to as well, and that's ultimately more critical. This is a new power for our species. Figuring out how to use it wisely is going to be one of our bigger challenges over the next 100 years.
One atom at a time. From medicine to materials, we're only beginning to glimpse the breakthroughs ahead. The challenge now isn't just building the technology, it's deciding how humanity will use it to shape a future worthy of its promise. And that future may be closer than you think. I came across a really interesting short story by Quantum called Valuable Humans in Transit, in which an asteroid hits Earth in a future where AI and nanotech are fully integrated into our world. I won't read the whole story, you should go and do that on Quantum's website. This is an excerpt from the story from the perspective of the main character, which is a sentient AI nanotechnology that saves humanity. The power of the universal constructor is this: to create food from burnt charcoal and water, to turn the entire Sahara into solar cells, to split a cubic kilometer of ocean into water, salt, and gold. I can literally build anything I can imagine, at any speed I can describe. I'm advanced enough to dream, though sometimes, in rising through the torrent of inspiration, here comes one of them. A dream, a wild idea. Save them. Gray gold spiderwebs erupt from car factories and food plants and desalinization tanks, and logging mills and smartphone screens and computer cores and waste disposals. All over the globe, all in my command. You got so lucky, Earth. A world built on nanotechnology is a world built on magic. You should go read the full story on Quantum's website. It's really good, and just a perspective on technology, and a perspective from technology I'd never heard before. Thank you so much for watching this video. It was a lot of fun to make and research. And as always, until next time, keep on building the future.